And when I joined my PhD, Spenter's age roughly was almost twice as mine. So like earlier students like Sanjay and Gautam, they describe Spenta as more like a person who is their friend, not much older than them, and going to trekking, etc., going to movies and staying in the same houses. But for me, Spenta was more like having an advising and parental role often. And I will tell a little bit about Spenta, that one thing Spenta always asks me is that, where are you? So often I'll come in the, you know that in TIFR we are a student in the DTP department, and in the DTP I'll generally come early, like 3 o'clock or 4 o'clock in the afternoon. That was early for me, and Spenta is possibly searching for me from 10 o'clock in the morning. And when I'll go there, my friends will tell me, you know, Spenta was searching for you. Where are you? Okay, I'll go and meet Spenta. And you know the Spenta is intimidating. So when I was walking, and DTP has a long corridor, Spenta's office was on the other side of this corridor, student room is on the other side. So while I was walking through this corridor, I often felt that, oh, that's the end of me. Okay. And so I'll go to his office and say, where are you? I said, no, I actually came at 10 o'clock. I was searching for you. Not really, but not always. I lied, but sometimes I had to. But to be honest, it was a very nice and illuminating experience to work with Spenta. One thing I learned from Spenta and liked about Spenta is that Spenta was always a very problem guy, the problem person, in a sense that Spenta was not super interested in just calculation for calculation's sake. Now, I don't want to be judgmental here, in a sense that this also, just doing a lot of computation, has its own value. So I'm not saying that it doesn't have, but what I liked about Spenta is that Spenta will, how he will work is that he will go through many things and sample many things and try to find what is interesting. He has bigger questions, like what is the entropy of the black hole. Now, those bigger questions cannot always be answered. But still, he would try to find some interesting question, which has some connection with those bigger questions, or generally interesting. So this, at least, I don't know if that's true or not. That's what I felt. That's how Spenta works. And I kind of liked and tried to learn this approach, try to find interesting problems in physics and outside physics and wherever it is, like many people before me describe it. So that was my experience with Spenta, and I kind of enjoyed the experience very much, at least the time I was there. When I was not here, Spenta was asking, where were you? Yeah. So it was a nice experience. I'll just describe a little bit about what I did. I mostly worked on large and gauge theories. So when I came in, Spenta was working there are various works, I think that Siraj Spenta, many people somehow initiated that line of work. So they were studying various matrix model and try to find matching between the phases of weakly coupled matrix model and phases of various gravity theories, etc. So Spenta already did some work when I kind of started working. And Spenta said that, okay, can you generalize it for charged black holes? And charged black holes, the phases of charged black holes are much more intricate than the phases, just the Hawking phase transition as phases of ordinary black holes, non-charged black holes in ADS. So there are many things like third order phase transition, this, that. And we found that in a very quickly that from this matrix model also, you can reproduce those phases very nicely. So that was my first work. And then I did a few other works with Spenta, and it was very interesting. So today I'm going to talk about something little different, but I chose this topic. This is a little bit older work. I also work in the similar things now, but why I choose this is that because this is something which is related to what I started with Spenta. And so I'll tell you the story and I'll go ahead. Okay, so what I'm going to talk about basically is that some work on the non-integrability of classical string world solutions, even for very simplistic cases. So let me give you some overview of the talk. So what is integrability or classical and quantum string integrability? I'll roughly follow this guideline, but not exact because I don't have much time, I think. So I'll basically jump up a little and let us just discuss that what is integrability. So in a very simple term, without going into much detail, is that for a classical system with n degrees of freedom to be integrable, there should be n conserved quantities. In the sense that there should be n conserved quantities such that their conserved charges, that their Poisson bracket with Hamiltonian is 0 and their Poisson bracket between each other is also 0. So basically, if you go to the action angle kind of variable, you can say that these charges are conserved, and sometimes, often, you can solve those theories. Not always integrability leads to solvability, but roughly I'm saying that that's the case. Now, why this is interesting is that there is a lot of work on the integrability of strings in ADS5 cross S5. As you know that because of holography, ADS5 cross S5 is one of the most popular string background, and solving string theory, at least the world sheet theory in that background, would be an interesting result. The first step, how people checked few things about holography, is that they have found that this string theory in ADS5 cross S5 has various kind of integrability properties, etc. And one can match from gauge theory side and from the gravity side. Now, interesting thing is that what happens is that generally string action in ADS5 cross S5 is some kind of nonlinear sigma models. And as found out by work by Penta, Suryanarayan, and Gautam, that these models at a bosonic level are integrable. Now, these results were kind of known before, that this kind of models are integrable, but the important thing was that they pointed out, look, ADS5 cross S5 also follows similar kind of models. String theory in ADS5 cross S5 are very similar, and they are also integrable, and that somehow initiated various works on integrability. And later people did various calculations from the gauge theory side, etc., and checked things with gravity. So roughly the idea is that if you have a Lagrangian which is like this, which is called corresponding conserved current, so basically Lagrangian which is like, and G is a member of some Lie group, small g is a member of some Lie group G, then what happens is that you can define some current like this, and you can define you can find this relationship hold, and taking the linear combination of star j and j, one can find the infinite number of conserved charges. So basically, if you write down string theory on ADS5 cross S5, you can see that at a classical level at least, you have infinite number of conserved charges. And one may ask whether these conserved charges, as I have said in the definition of integrability, whether these conserved charges really commute with each other. I think that's not what they found, at least in these works, but later people have shown in many cases they do. That's my read on this subject is. And later Bena, Polchinski, and Roiban, they generalized it in the next year for the fermionic case. So if you take superstring theory, they have also shown that these conserved charges still exist in the superstring theory. So in the classical level, superstring theory is integrable. Okay. So there are many aspects of integrability and why it's important. I'm not going into that in this moment, but later I'll describe them. So what Spenta asked me is that, okay, so we have seen that string theory in ADS5 cross S5 is integrable. So let's do something a little more. The next question one may like to ask is that, okay, string theory in ADS5 cross S5 is integrable, fine. What about a background which is little more complicated than ADS5 cross S5? And one such background is called E11 geometry. So this is like, so I don't have, so time to describe all the geometries very properly, but basically the concept is that ADS5 cross S5 is an ADS space and a product of S5, that is sphere. Now, we know that this sphere can be replaced by other geometries. Other geometries in higher dimension, there are other geometries which is constant Ricci curvature, just like sphere. So one such example is this geometry, which is called T11 geometry. Has been so this is also a 6-dimensional geometry, and this is not a sphere. This is but this still has a constant Ricci curvature. I mean, the curvature is same everywhere in this geometry. And people have discussed string theory in this space. The one natural question is that if we take a little bit of generalization of string theory and describe and try to study bosonic string theory, very simple thing, like classical bosonic string theory in this kind of background, would that be integrable? So I guess we tried to do a little on this problem, and there is some generalization of it called conifold, etc. We tried to do something, but it didn't go anywhere, so kind of abandoned it for some time. And then later, now, if you look at a motion of a test particle rather than a string, rather than a string, if you just look at a motion of a test particle, the one single particle moving in some complicated background, that won't even be integrable. Like if I throw a ball in this room, there's a lot of potentials there, say something is going, a lot of bodies are there, say they are gravitationally affecting some test particle, and motion of such a complicated thing would not be integrable. So there is no surprise. So this is like, I have drawn a type of Venn diagram, like multi-center black holes, etc. The motion of a test particle generally in these complicated geometries are not integrable. Now, if we look at a very nice space, like say sphere, or a flat space, or just ADS5 cross S5, then motion of a single particle in those geometries would be integrable. But what happens that, but the geometry I just described before, like this geometry, this is also nice enough so that motion of a single particle is integrable in this geometry, wave equation is separable, and so this is a nice geometry. The question is that this is a nice geometry for a test particle and wave equations. What about strings? If you look at motion of the classical strings in the geometry, how do they behave? So we'll find the question is that is there a space between these two spaces, this space of non-integrability, very nice space, everything, even string motion is integrable. What about this space? Whether some motion is whether is there a space where string motion is not integrable but particle motion is? Now one should point out that in classical limit, motion of a single particle is kind of like a limit of a string when size of the strings becomes 0. So motion of a single particle is actually a subset of the string motion. So that's why this set is a proper subset of the whole thing sitting outside. Okay. So what we did is that if we want to see that what the motion is, let us study a very simple configuration of strings in this geometry. So what can be that simple configuration? One simple configuration is that you see that there are two cycles here, like d psi, cos theta I, d phi I whole square. So let us do one thing. So this is phi 1 and phi 2 are two S1 circles. So let us wrap a string in this geometry. This is a 6-dimensional geometry, little difficult to visualize. Is that what I did is that we wrap in one circle for alpha 1 times and in other circle for alpha 2 times. And we choose a gauge where world sheet time is same as this time, world sheet psi is same as proper psi. We choose such a gauge. And then you basically have two things in your equation, theta and psi kind of decouples and becomes j square, psi dot square. So there is a couple equation. What you get at the end of the day is a couple equation of these two thetas, theta 1 and theta 2. Okay. So this is the couple equation, and that's how the Hamiltonian constant looks like. So theta I dot square and alpha I sine square theta I and alpha 1 alpha 2 cos theta 1 cos theta 2. But to be noted is that if alpha 1 of them, if it is 0, then one theta completely decouples from the equation, because there will be no cross term if one alpha 1 and alpha 2 0. So we have two different completely separated motion, and in those two one-dimensional motion, and both of them will be integrable, because all one-dimensional system theta I square plus v theta are integrable. And the important thing is that for a test particle, if you look at a test particle in this geometry, we would not see this potential term. We may see the other things, but not this potential term. Okay. Now, from this Hamiltonian constant, it's not very difficult to find out the equations of motion. The equations of motions are just like this, just like a simple equation of motion. And if you plot this potential, the potential of V1, V theta, it looks like a potential which has some kind of symmetry, but is not very symmetric also. It has a maxima and 4 minima, and they get repeated. So, and if one of the theta 1 is 0 or pi, then also the equations are decoupled, and we can again analytically solve it. The question is that if we start from generic condition, what happens to this kind of model? Okay, so what we did is that just, these are not that difficult to simulate in a computer, just two coupled ordinary differential equation. So one can see that what kind of solutions they have. And one would find that, this is just a solution from a random initial condition. So this solution doesn't tell you much, but I just show you is that if you just start from a random theta 1 0, theta 2 0, and evolve through those equations I have just shown you, what kind of thing you get. Now these equations to be noted as a very simple physical interpretation. So if you look at just theta I square plus sine square theta I, this is more like a potential for a pendulum. So theta 1 square, pendulum in a gravitational field. So theta 1 square, so theta 1 and theta 2, it's like two pendulums which are not just parallel to each other, and not parallel, perpendicular to each other, moving independently. And this term somehow what it does is that you somehow connect them with the spring. So one pendulum is moving in XY plane, another is YZ plane, and you somehow connected them with spring. It's a double pendulum connected by spring. This is a very intuitive physical interpretation of this potential. Now we know that these kind of things are generally not integrable. Not only that, they would show the signature of chaos. So, so basically what will happen is that if we look at, so this is the minimum of the potential. So if you look at a motion which is near this minimum of the potential, then quadratic approximation in this potential is kind of valid, and we see very nice motion like small fluctuations in pendulum, and those motions will look like not chaotic. But once we increase the energy, we guess that this motion will become more and more chaotic. So small values of P, we see a periodic or quasi-periodic behavior of the motion. Large values of P, the periodicity is lost. The hints at the fact that the motion becomes chaotic. So basically, to see the chaos, what we'll do is that we'll look at the Poincare section. So what is a Poincare section? And generally, so before going to the Poincare section, let us see that there are four parameters here, theta 1, theta 2, and theta 1 dot and theta 2 dot. So it is a four-dimensional space, right? So if the system is integrable, so one concept quantity is always there, which is energy, And if there is another conserved quantity, Hölderlin have two conserved quantities, four-dimensional space. So the manifolds where the motions are kind of confined will be two-dimensional. So if we take various cross-section, two-dimensional cross-section of this four-dimensional space, then these two toruses will somewhere, not four-dimensional space, we look at the constant energy surfaces, which are a three-dimensional space, and these two toruses, and look at some cross-section of this, in these two toruses, this will means cut this, will actually overlap with this equal energy surfaces in various kind of concentric circles or ellipses. So basically, if you look at the various toruses, you take a cut, a series of cylinders, you take a cut, you will see various concentric circles if the system is integrable, if there is another conserved quantity other than energy. Okay, so there is some discussion about KAM theorem, etc. I'm not going there. So basic point is that, so if we look at a small energy solutions of this theory, we'll see that this cross-section, a phase-phase cross-section, shows very nice this circular or toroidal structures. Means that if you cut this ellipsoid structures, so as we increase energy more and more, what we'll see is that these toruses are getting dissolved in certain ways, and we do not see nice, is that these trajectories we'll see with, which are plotted with different colors, have different initial conditions but same energy. Okay, and these trajectories with different initial conditions do not overlap with each other. But here what happens is that you see that this trajectory, that this one is getting a little bit hazier. So there is no nice manifold structure around. And now in this picture, as you increase energy more and more, you will see that these trajectories are kind of getting dissolved. And this is a very visible chaos that these trajectories are colored differently, and points with different colors are kind of getting mixed up. And here you see that points with all the colors are kind of getting mixed up. Here is a complete chaotic thing. As we increase energy again, we see the formation of the order, and at a very high energy, order is again formed. So what we see is that the system goes through a chaotic transition and goes from an ordered state to another ordered state. Why do we see that in this ordered state? It's easy to understand why we see is that as the energy becomes higher and higher, this potential term, the whole potential terms is negligible. This actually becomes a free particle moving. And that is why at a very high energy, we again find some kind of predictive behavior. So these KAM theories, generally this is called KAM theories, show a clear signature of the chaos. So it seems that if for a very simplistic case also, motion of a strings in T11 background, even a simplistic configurations, are very chaotic. And we can also calculate Lyapunov Index and things like that, and we find that Lyapunov Index is non-zero. I'm not going to the definition of this Lyapunov Index, but Lyapunov Index is almost like 0.25, etc. Now, so the system is chaotic. Somehow, in a more informal term, we may say that system is also not integrable, but it is better to have an analytic proof that even these simple equations of motion are non-integrable. So that's also did in some of our other paper, is that if you look at this potential, there are few solutions which can be exactly solved. It is that if one thing goes over and over like this, these solutions are exactly solvable where one of the variables theta 1 or theta 2 has been put to 0 or pi. So things going over the top and coming back, over the top and coming back. So this just moving in one direction. So the question is that now you take that solution, theta 2 is equal to pi, and theta 1 is equal to this. This is an exact solution. Now if we expand a little around that solution, So we expand like theta 2 is equal to theta 2 plus some eta or something. And theta 1 is given by this solution. Now what happens is that, which is called normal variation equation for theta 2, is this equation. Now this is completely second order equation with some time dependent coefficients. And one can put cos theta 2 is equal to z to find out an equation which is a second order equation of eta where all the coefficients are polynomials in z. Now given that all the coefficients are polynomial in z, so we can exactly calculate fz and various fz, f dash z, and this is also a polynomial. So given that, there is some algorithm called Kovacic's algorithm which finds out if this second order differential equation has a fast integral. Not all second order differential equation has a fast integral. Some has. Like if you look at a motion of a particle in just one dimension coming from a Hamiltonian, this equation has a fast integral which is the Hamiltonian itself, h is equal to constant. But if you write down a generic second order equation, something into theta dot dot plus something into theta dot plus something is equal to 0, it is not necessary that this integral will have an fast integral. So the question, if the system is integrable, we expect these equations to have a fast integral other than the energy constants which we have already used. So there is an algorithm called Kovacic's algorithm, a systematic procedure for calculating the fast integral of the second order differential equations with polynomial coefficient if it exists. So we basically, this is a complicated algorithm and use various things in Galileo's theory and things like that, which I do not know very well, but there are programs which goes through this thing and determine if your theory is integrable or not, with this equation. So we use that algorithm to check that our simple model, in our simple model, this algorithm fails unless alpha 1 or alpha 2, some of them is 0. And then the system actually separates. So using numerical analytic methods, we have found that string theory in the T11 background is non-integrable. So it seems that the string theory, string motion, classical string motions are not integrable and more chaotic than a particle motion, even in very simple and symmetric backgrounds. One is T11, even the Schwarzschild black holes, ADS Schwarzschild black hole, ADS solution, D3PN backgrounds, etc. People have shown that later. Even in those backgrounds also, the very simple configurations of string motions are not integrable and chaotic. People have shown various things. So we haven't really considered worldsheet fermion in this thing, so that will be one interesting thing. And of course, we later studied the quantum integrability, and what we did, we look at some mini superspace approximation of these full Hamiltonians and try to see that what kind of spectrum it has. It actually shows various properties of the quantum chaotic system, which I am not